Good morning. Once again, my name is Scott Deutsch, and I'm the Manager of Communications and Brand here at America Makes, and I'll be your host and moderator for today's America Makes TRX webinar series. Just a little bit of background on the TRX webinar series before I introduce our speaker. As America Makes continues its mission to expand and accelerate the footprint of additive manufacturing and 3D printing, we've created this medium called the America Makes Technical Review and Exchange Webinar Series, or TRX webinars. By creating this platform, it allows the additive manufacturing community to come together and share knowledge and experience with a broader community. If you or your team are interested in presenting during a webinar, the TRX webinar, there will be a link at the end that you could complete a request form and contact, or you could contact America Makes Membership Director Tiffany Westbay directly. Just a few housekeeping items here as we kick off today. At the end of the presentation, there will be an opportunity for a brief Q&A. If during the presentation you have a specific question that comes to mind, please submit it in the Q&A space on the WebEx screen, and we will get it answered during the Q&A session. We'll do our best to get everyone's questions answered, but please use the Q&A space so we can track them a little bit better. I see there's some people posting questions there now. So let's just get started. Today's webinar, today's TRX webinar is going to be given to us by Zach Simkin. Zach is the president of Senvol. Senvol is the industry leader in data for additive manufacturing. At Senvol, Zach has spearheaded the creation of the Senvol indexes, which are the first commercially available data sets for additive manufacturing material characterization. Today, Zach, during his presentation, is going to discuss Senvol's approach to generating, accessing, and analyzing pedigreed data for additive manufacturing. Zach will showcase Senvol's machine learning software for AM, which is being developed for the United States Navy. This software analyzes the relationships between additive manufacturing process parameters and material performance. And without further ado, I'd like to introduce my friend and colleague, or my friend and member of America Makes, Zach Simkin.
Thank you, Scott. I appreciate the introduction. Before beginning, I certainly want to thank America Makes for hosting this webinar series. You guys have all been great partners of ours. And I'd also like to thank each of you who have dialed in today to the WebEx. I appreciate you taking time out of your day to join us. So what I'll be talking about today is our approach at Senvol to generating, accessing, and analyzing additive manufacturing data and our solutions for that. Real quickly on the agenda, I will give a brief overview about Senvol. I will then discuss our approach to access, generate, and analyze additive manufacturing data. Really quickly, I will go over services that we offer, and then at the end, I will open it up for any questions that you have. So I'm sure many of you are aware or would agree on the call that additive manufacturing is changing how products are designed and manufactured in countless industries. And we at Senvol believe we're just at the tip of the iceberg. And at the epicenter of the entire industry, in our opinion, is data. It doesn't matter if you're an end user, a material manufacturer, a software provider, all organizations in the additive industry need and rely upon data for their additive manufacturing initiatives in one way, shape, or form. But data for additive is hard, and it's a big fundamental problem for the entire industry. And Senvol is solving this problem, and it's the global leader in data for additive manufacturing. Senvol is a globally recognized brand in additive. Here's a quick look. It's just a small handful of companies and organizations that use and trust various Senvol products. We've been covered and featured in various media publications, everything from industry publications like engineering.com and Design News to larger publications such as the Chicago Tribune. And outside of what we do at Senvol, we're also involved in various organizations in the industry. As Scott mentioned, we are members of America Makes. We also have members who serve on the ASTM F42 committee, which sets standards in the additive manufacturing industry, as well as the SAE Additive Manufacturing Committee, which is another committee that is setting standards in this industry. So now I'll go over our approach to access, generate, and analyze additive manufacturing data and our solutions in each of these areas. So all of our products are data related in the additive manufacturing industry, and they all tie into the same problem statement, which is that access to reliable additive manufacturing data is very hard. And without this data, companies cannot adopt additive manufacturing. And everything we do ties into solving and helping to solve this problem statement. So our products fall into three buckets. The first is providing access to additive manufacturing data. The second is a product to help companies generate their own pedigreed data for additive manufacturing. And the third is software that helps companies analyze additive manufacturing data. So these solutions are called the Senvol Database, Senvol API, and the Senvol Indexes. Those are different database products, which I'll be going over in a little more detail in a minute. Our solution to helping companies generate data is called the Senvol SOP. And our software to help companies analyze additive manufacturing data is called Senvol ML. And that is our latest machine learning software for additive that I will get to at the end of the presentation. But at first, I will start by going over the Senvol Database. So the problem statement specifically for the Senvol Database is that it is difficult and time-consuming to search for data on additive manufacturing machines and materials, particularly in a rapidly growing industry such as ours, where there are constantly new machines and new materials coming out all the time. So the solution to this problem is the Senvol Database, which many of you may be aware of. It is a comprehensive database of industrial additive manufacturing machines and materials. I emphasize the word industrial because the Senvol Database only tracks industrial equipment. It does not track desktop machines or desktop materials, only industrial machines and industrial materials. And what I'm going to do now is actually just show you a live demo of the Senvol Database. So the Senvol Database is on our website, and it is completely free to access. So I encourage many of you who may find this useful to go check out our website afterwards and use this resource as often as you'd like. So it's on our website. You just go to senvol.com/database. And as I mentioned, it's free to access. And because this is free to access, it's actually one of the most used resources in the industry. We have thousands of global users every single month coming to use this resource. So within the database, there are two types of searches. There is a machine search and a material search. And I'm going to start by showing you the machine search. It's fairly straightforward. You can search for machines by the specific machine manufacturer, by the specific machine model if you know that. You can search by the additive manufacturing process type, and we use the 7 processes as defined by ASTM. You can search by material type. So for example, if you want to find a machine that accepts titanium, you can do that. You can search by the size of the build envelope. So let's say you have a part that needs to be made by titanium and you need a build envelope that's at least 10 by 10 by 10. You can search by that. And lastly, if you'd like, you can search by the price of the machine. And then you click Submit, and it takes me to the results table. So these are all the machines that accept titanium that are at least 10 by 10 by 10 in build envelope size. So as a user goes through this, if there's a particular machine that seems of interest and you want more information on, let's say this example here, this RCAM Q20 Plus machine from RCAM, you can click for details. And then now it takes me to the details page for this RCAM Q20 Plus machine. It starts by showing some general information about the machine. It then shows a table of materials that are compatible with this machine. And it does not only include materials provided by the machine manufacturer, but we include third-party materials as well. So in this case, you'll see Hoganov has a Ti64 material that is compatible with this RCAM Q20 Plus machine. And then lastly, there's just some additional information about the machine, the size, the weight, electrical usage, and so forth. So that's the machine side of things. I'll now show you the material search. It is fairly similar. You can search by material supplier, the name of the material, again, the process type, or the type of material. You can also search by mechanical properties. So for instance, if you want to search by a tensile strength or elongation of break, you can input a min and or a max. You can search by hardness, by some thermal properties, physical properties, and lastly, a few certifications and tests. When you're done, you click Submit. I didn't input anything in, so it's just going to show me the universe of all the industrial additive manufacturing materials. And as you go through this, if there's a material that looks to be of interest, again, let's say this 3D Systems Acura 25, I will click for details. And it takes me to the details page for this Acura 25 material. It starts with some general information. There's now, converse to before, there's now a table that shows which machines are compatible with this material. And then it shows the material properties. So the tensile strength, modulus, elongation, so on and so forth, heat deflection temperature. And lastly, if it's reported, we include and show the bulk material information. So that's the material properties of the feedstock before it has been processed. So again, this is free to use on our website. I encourage all of you to check it out if it's useful. The data in the Senvol database is provided to us from the machine and material manufacturers. So the data in the Senvol database is not generated by Senvol. It is not validated by Senvol. It is as provided to us from the machine and material manufacturers. Next, I'm going to go and talk about Senvol API, and we're still in the access additive manufacturing data bucket. So the problem statement for the Senvol API is that access to additive manufacturing raw data is required for various additive manufacturing software functionality, but it's expensive and time-consuming to collect this raw data. So the solution here is that we actually provide paid licensing options for companies that want to access the Senvol database raw data. So what I just showed you is free to access on our website, but if you want all the raw data to integrate into your software or platform, we do provide licensing options. Some examples of the types of things that companies use our data for when they integrate with the Senvol API is there are companies that provide you, will connect you to service bureaus if you're a company that needs to have a part made by additive manufacturing. And when you're on that website, you maybe select what machine and material you want to use. Those vendor sign-up drop-downs can be powered by our data. We've integrated with a CAD vendor where the designer selects what machine they're designing their part for, and then the bounded box size of the machine automatically populates in the CAD environment, so the designer knows if the part is too big or too small. Again, that data and functionality is powered by the Senvol database data. And another example is materials management software integrate with the Senvol database and provide material analysis so that you can analyze and plot graphs and charts with that data. So some examples of integrations we have partnerships with Granta. Granta, if you are not familiar with them, they are one of the leaders in materials management software, particularly for additive manufacturing, and the Senvol database data is available through the Granta software to do analysis on. The United States Air Force is another example. They had integrated with the Senvol database data into their HyperThought platform, which is their materials management solution. A third example is HP. HP is a slightly different use case. They actually integrated with the raw data for competitive analysis reasons. They want to look at and analyze what all their competitors are doing and how their machines and materials stack up against their competition. And then a fourth example is the Defense Logistics Agency, also known as the DLA. The DLA is the acquisitions arm for the United States Department of Defense. So they buy most of the products and parts that go across the DoD. They have millions of products that they procure, millions of SKUs. And what they did is they developed a tool, they call it an additive manufacturing part candidate tool. And the tool assesses these millions of SKUs and figures out of the millions of SKUs, which subset of those parts are potentially candidates for additive manufacturing. And the functionality of that tool was largely powered by the Senvol database data. I'm now going to move on and talk about the Senvol indexes. The Senvol indexes are a completely different type of database that I will be talking about. So this is now separate from the Senvol database and Senvol API. The problem statement for Senvol indexes is that additive manufacturing materials are complex, and in-depth data is really needed in order to be able to use the materials. But generating this data is difficult and expensive. So the solution is Senvol indexes, which are the first commercially available data sets for additive manufacturing material characterization. And this differs from the data in the Senvol database that I just showed you. So data in Senvol indexes is pedigreed, traceable, in-depth data that we, Senvol, have generated on our own. So the Senvol database data I showed you is data provided to us from the machine and material manufacturers. Senvol indexes data, which I'm now going to show you now, is data we generate that tends to be much more in-depth than the data you'll find on the spec sheets. So what I'm going to do now is get out of the PowerPoint again and show you a little more details. So what I'm showing you now is the cover page of a particular Senvol index. Every Senvol index data set is a combination of a specific material when processed on a specific machine. So this cover page is for a particular Senvol index that was Ti64 from AP&C, processed on the RCAM Q20 machine. We at Senvol do not own any of the equipment ourselves, so we contract the manufacturing with AS9100 certified facilities, and we have testing done at NADCAP and A2LA accredited facilities. For those of you that are not familiar with those levels of accreditation or certification, they are essentially the highest levels of accreditation in the aerospace industry. So in layman's terms, this is another way of saying that we use the same vendors that large aerospace companies use. And what's included in these Senvol index data sets is three main components. The first component, which is in this blue box, are the test specimen properties, and I'll get into that in a minute. The second component are all the process parameters. So we don't just show you the properties, but we show you the quote-unquote recipe that we use to achieve those results. And lastly, in this third box down below is a summary of some of the feedstock properties. So we characterize the feedstock for every single build, and all of that data is included as well. So for this particular Senvol index, again, it was TIE 64 from AP&C processed on the RCAM Q20. What you're looking at here in the middle is the test matrix. So this was the testing that we did. So for example, we did tensile testing and we built 48 specimens. There were 16 as built, 32 were hipped. There was fatigue testing in this case, hardness, compression. The test matrix varies from one Senvol index to the next. They don't all follow this test matrix. It depends on the demands of our customers. So this is just one example of the types of test matrix we might do. In this case, this was done across 4 different builds. And we had orientations for specimens of X, Y, Z, and X, Y 45 degrees. Down here is an image of what the build looked like, and the build file is also included as part of the Senvol index data set. So this is the cover page. I'm going to show you some examples of the types of information that is included in a Senvol index data set. And I will start by showing you a process control document. So this process control document is an example of one we use for the RCAM Q20. And this is where we capture and track all the parameters that were used for building of the specimens. So we characterize a lot of information about the feedstock. That's this first section here. It includes things such as, obviously, the feedstock supplier name, but also the powder production method, the heat number, the lot number, the apparent density and tap density, the flow rate. Some information refers to files that are too large to fit in this one document. So you'll see here the feedstock recyclability schematic is something that we track, but that is tracked on a separate document, which is just referred to here. We include chemical analysis, particle size distribution. So that's on the feedstock. There are then a whole host of parameters we capture on the fabrication. And again, this is example specific to the RCAM Q20 machine, which is an electron beam melting machine. We include, obviously, the serial number of the machine, the filament serial number, software that was used, information about the maintenance, information about the beam alignment, information about the slicing and the build platform. I'm just calling up, kind of random examples of the many variables we track. Information about the layer thickness, the recoding speed, the cool down time. We essentially track any and every variable that may impact the results. If we're not sure if a variable will impact a result, we still track it just so we have that full traceability. So all this information, and then lastly, all the information about any post-processing that was done is also captured. In this case, we hipped some of the specimens, so that is also included on the process control document. In terms of what the data looks like itself, it comes in Excel files. And again, these come as specific data sets. They're purchased individually, not as a compilation. So this particular Senvol index data set would look like this. The values themselves have been redacted. So that's why these cells are blank. What we're looking at is what would have been tensile results for X orientation specimens. Every single individual data point maps to a sample ID. And the sample ID then maps to the build file. So you can see every single data point exactly where in the build it came from, which build it came from, and what all the parameters were for the build that made that specimen. And the specimen IDs have meaning. So the X here is referring to an X orientation, B is referring to a specimen that was in the back of the build envelope, and 1 is referring to, in this case, build number 1, because we had 4 builds. So there's tensile data, compression data. In this case, we also had fatigue data. Again, the values have been redacted. We include a curve, although many companies want to plot their own curve, which is why we provide all of the individual values. We include metallography, so microstructure images. Again, the images have been deleted, but all the microstructure images would be included in a Senvol index as well. And lastly, we also include all the stress strain values, because again, a lot of companies want to plot their own graphs. So let me go back in now. So that was an overview of Senvol indexes. The business model for these Senvol indexes, really quick, is fairly simple. We sell a Senvol index, each individual data set, for a fraction of the cost of development. So for our customers, they're able to get this pedigree data much quicker and much more cost effectively compared to generating the data on their own. And for us, we're able to do this because we sell the same Senvol index data set to multiple companies. So once we sell a sufficient number of them, we get a positive return on our investment. In terms of what companies use this type of data for, there's typically a few use cases. One is to just make a go or no-go decision on adopting additive. Another is to decide which machine or material to use. So after you've used maybe the Senvol database and you look at spec sheet data and you maybe find there are 6 materials that might meet your application need, at that point you tend to want a little bit more in-depth data, and so this data can fill that need. Senvol indexes data has been used for designing parts, for simulating additive manufacturing part performance, and lastly, can be used for optimizing machine settings. So that concludes the section on accessing additive manufacturing data and our different database products. I'm now going to move over to the second bucket, which is helping companies to generate their own pedigree data for additive manufacturing. So maybe we don't have the data you need, or for whatever reason you want to generate your own data. We have solutions to help in that area as well, and it's called the Senvol SOP. The problem statement for the Senvol SOP is that generating pedigreed additive manufacturing data is extremely complex and difficult. And just some examples of the complexities that need to be thought through include things like you obviously need to plan what you're going to fabricate, how many specimens you're going to do, what tests are you going to do, what will the sizes of the specimens be, how do you select appropriate vendors, whether it's internal or external vendors, how do you capture all the process variables, what standards are you going to use, what do you do when industry standards don't exist, how are you going to handle the material, how will you recycle the material, how are you going to maintain and calibrate your machine, how are you going to appropriately post-process your specimens, and then it's kind of circular because how does post-processing then go back to affect your planning? It may affect the number of test specimens you want to build, it may affect the build layout, so on and so forth. And the real pain point we're trying to solve is a company, let's say, has an additive manufacturing data generation project, and we will call it Data Generation Project A. This project has a lot of people involved. So Joe might be your M&P engineer, Fatmata might be your design engineer, you might have a mechanical engineer named Bob involved in the project, Sarah's involved, she's your program manager, you might have someone from the leadership team named Lou, and then you might have a manufacturing engineer named Jess involved in this project. So all these people are involved in just one additive data generation project, which we're calling Project A. But for larger companies in particular, they might have multiple projects going on. So there's Project B going on. It could be at the same site, maybe it's at a separate site, but there's going to be a whole host of different people involved. And then you have Project C, D, and so forth. When you have all these projects and all these different people, what I'm getting at is that there are a lot of stakeholders involved in pedigreed additive data generation projects. And without a standard operating procedure that dictates what should be done when you're generating pedigreed data, at the best case scenario is that you're going to end up with inconsistent data. So even if everyone is very well trained and very well intentioned, just by nature of the fact that you have so many people involved across different sites, different people are going to do some things differently, and that can lead to having data that is inconsistent and you can't necessarily compare from one data set to the other, and that's a problem. The worst case scenario, of course, is you might actually end up with unusable data. So this would be a case where you may have employees that are not fully aware of all the steps that they should be doing, and they might leave things out or miss steps, and that can actually lead to data being totally useless. There's an example I know, and this is a true story, of a very large, well-respected aerospace company that spent $1 million generating a data set. After the fact, they realized they had not tracked all the process parameters that they should have tracked, and they couldn't go back in time and find out what those process parameters were. So this $1 million data set ended up actually being useless, and they essentially had to throw it in the garbage because they weren't sure the process they used to achieve those results. So the solution to this problem is that we've launched the Senvol SOP, which is it's a manual, it's a physical manual, a document that documents processes and procedures for generating pedigreed data. It's about 100 pages long, and it walks a user through step by step, literally every step that you should follow when generating pedigreed data. The impetus for the Senvol SOP document actually was the Senvol index data sets I showed a few minutes ago. We've been generating these data sets for years, and very early on it became apparent that if we wanted to have consistency across our data sets so that we can compare and contrast, we needed to make sure we were generating these data sets in a consistent manner. And so we developed the Senvol SOP for our own purposes for generating pedigreed data internally, and we've been using it actually as a trade secret for many years. Recently, though, we sort of came to the realization that this document likely has value outside of just Senvol and would likely be valuable to many others in the industry. So we made the decision to go ahead and commercialize the Senvol SOP manual and make it commercially available for sale. We didn't, by the way, just develop this manual in a vacuum. It took us over 3 years to develop, and we incorporated feedback from over 250 companies. Here's a look, just the manual itself. That's the cover page. And then very recently, as I mentioned, we made the decision to commercialize it. And the first step in that process for us was to get third-party validation. So we had been using this document for years ourselves, and we thought it was great. But maybe we had rose-colored glasses, and the document was not as good as we thought it was. So we partnered with Oak Ridge National Lab last year, and continuing on into this year. And our partnership with Oak Ridge National Lab is we provided them access to the Senvol SOP document, and the purpose was for them to provide feedback to us and now also integrate it in their data generation projects. And the feedback was overwhelmingly positive. They now have adopted and are using the Senvol SOP for some of their data generation projects. So we've gotten this third-party validation that we were looking for, and so we did commercially launch the Senvol SOP just recently at the AMUG conference a couple of months ago. In terms of what's included in the Senvol SOP manual, again, it's 100 pages that documents step-by-step how to generate pedigreed data. The types of topics that it covers includes things like test plan procedures, fabrication procedures, cost estimation consideration procedures, templates for fabrication, test, and cost estimation, standards to follow, vendor selection processes for fabricators, post-processing vendors, and also testing labs, parameter capture procedures, data development procedures, data collection and compilation procedures, document management, and lastly, an overall flowchart. The document itself is broken down into 4 main sections. Section 1 is all about planning. Section 2 is about standards. Section 3 is about vendor selection. And Section 4 is about information flow guide. So in layman's terms, what this is Section 1 is all about what are you going to do. Section 2 is how to do it. Section 3 is who will do it. And Section 4 is the order in which it will be done. A look at some of the specific subsections within these. Section 1 includes 1.1 is about the test plan. 1.2 covers everything you need to know about your post-processing plan. 1.3 is all about the feedstock plan. On the standard side, there's a whole section on process control documents. There's a section on feedstock recycling standards, on fabrication specimen labeling standards. The vendor side has checklists for everything you should consider when selecting vendors. And lastly, on the information flow guide, there's some documented task trackers. So again, the Senvol SOP is meant to ensure that every step in a pedigreed data generation project for additive manufacturing is done and documented appropriately. It is literally a step-by-step guide that walks the user through everything that needs to be done and every best practice along the way. What the Senvol SOP is not, and I want to be clear on this, it is not prescriptive. So what I mean by that is I'll give an oversimplified example, but one step in the Senvol SOP tells the user to determine and document what test standards the project will follow. The Senvol SOP does not, however, tell the user which standards to follow. That is entirely up to the user to decide because it depends on the specifics of the project. So that's what I mean by saying the Senvol SOP is not prescriptive. In terms of the benefits, I think I covered most of this, but implementing a Senvol SOP or some similar standard operating procedure in your company will ensure that you save money, save time, that all your employees avoid making what can be critical mistakes, and most importantly, is that you're documenting the entire process in a pedigreed or traceable manner. So that was the Senvol SOP. That was all about generating pedigree data for additive manufacturing. And I'm now going to discuss the third bucket, which is analyze additive manufacturing data, and I will be discussing our machine learning software in this space. So how do process parameters impact material performance? Answering this question is one of the U.S. Navy's main goals with respect to additive manufacturing, and in a minute I'll get to why I'm calling out the U.S. Navy specifically. But in order to answer these questions, the Navy has resorted to following a pretty painful process, which is using trial and error and design of experiments. I'm sure many of you have experienced this pain point firsthand yourselves, but the problem with trial and error and design of experiments is very clear. It's extremely expensive and time-consuming. What the U.S. Navy wants to do is to be able to analyze the data that they've already generated and to learn from that data in order to reduce the amount of trial and error and design of experiments that they need to do. To accomplish this goal, the Navy has hired Senvol to develop data-driven machine learning software for additive manufacturing. The software will be made commercially available not just to the Navy, but to any company or organization. And what I'm going to walk you through today is the background to our data-driven approach, as well as some of the Navy's use cases for our software. The first use case I'll highlight is determining what process parameters to use in order to achieve a target mechanical performance. So this is a case where the Navy has, let's say, a target fatigue life in mind for a particular application, and our machine learning software can tell them what process parameters to use on their machine in order to achieve their target fatigue life. The second use case is about the use of in-situ monitoring data to simulate non-destructive tests. The third use case is about predicting material properties and mechanical performance. So the third use case is actually the inverse of the first use case. The third use case is where an example where you know what your process parameters are, and based on those process parameters, you want to predict what maybe your tensile strength will be, for example. And the fourth and final use case I'll talk about today is a concept called transfer learning, which is where the Navy can learn and apply learnings from particular machines and materials and that data and apply those learnings to different machines and materials. Everything I'm going to show you today in terms of examples are real actual results that the software has achieved for the Navy. None of this is hypothetical or theoretical. These are all real results. Just a quick background on why I'm talking about the Navy so much is that this machine learning software that we've been developing is being co-funded by the U.S. Navy through what's called an STTR program. STTRs have multiple phases. We've already completed phase 1 of the program. We are now in the midst of phase 2, and once we complete this phase 2 program, the software will be made commercially available. Just a really quick background for those of you that might not be familiar with the concept of machine learning. Machine learning is a type of artificial intelligence that allows the computer to perform a task, for example, recognize a pattern or make predictions, without being explicitly programmed to do so. The computer learns to perform the task by being trained using training data. So, for example, a training data set that includes information on process parameters such as laser speed and laser power, and process signatures such as melt pool depth can be used to train a machine learning algorithm to predict melt pool depth based upon a given laser speed and laser power. So the way our Senvol ML machine learning software works is we modularize additive manufacturing data into 4 modules. The first module, module 1, is all about process parameter data. So this includes things such as laser power or scan speed. It also includes the characteristics of the feedstock, for example, the chemistry and the particle size distribution. That is all included in module 1 data, process parameters. Module 2 data is process signatures. So this is in-situ monitoring data, essentially, so things such as melt pool temperature and melt pool depth. The third module is material properties. That includes things such as microstructure or surface roughness. And the fourth module is mechanical performance. So that's data such as tensile strength or fatigue life. And the way our software works is it can take data from any one of these 4 modules as an input, and then make any one of the other 4 modules a predicted output. So for example, what you see on the screen here, F12, we refer to as function 12. This is a case where data from module 1 is an input, and what we're predicting is data from module 2. So in this specific example, laser power is an input, and what we're doing is predicting melt pool depth based on laser power. Our software can also obviously do F23, it can do F34, but it can also do inversions, as I mentioned earlier, which is really nice. So F41 is an example, again, as I mentioned earlier, where you have a target fatigue life, and that is actually your input, and the output is predicting what process parameters to use in order to achieve that fatigue life. This approach of modularizing additive manufacturing data is not unique to us. Some of you might be familiar with it. It's been used in industry before, and it tends to be used for two different types of approaches. One is a physics-based approach, which is not what we are taking at Senvol. It can also be used for our approach, which is a data-driven approach. Physics-based approach and data-driven approaches we feel are very complementary. There are kind of reasons you would use one or the other. For those of you that aren't familiar with these distinctions, in a physics-based world, inputs and rules such as formulas go into a model, and what you get are predicted outputs. Whereas in a data-driven world, inputs and outputs are both what go into the model, and what you get, what you're predicting, are inferred rules. So for example, inputs in a data-driven approach can be the additive machine parameters, and the outputs can be tensile strength. All of that will go into a machine learning model that then infers the rules or relationships between those inputs and outputs. And again, we think these approaches are complementary. There are certainly pros and cons to both, and reasons you would want to use one approach over the other. The biggest benefit by far to a physics-based approach is causation. So physics-based simulations, of which there are several really great ones in the industry, show causation, and that's really good. The reason we have taken a data-driven approach is that there's a fewfold. The first of which is not the reason. And what I'm showing here on the screen is actually the biggest con of a data-driven approach, which is that data-driven approaches only show correlation. They don't show causation. But the reason we took a data-driven approach is that our software, our machine learning software, because it's a data-driven approach, can actually apply to any additive manufacturing machine, any additive manufacturing material, or any AM process. Whereas physics-based approaches need to be specific to, for example, the particular energy source, the particular process. Our data-driven approach can be applied and ingest and analyze data from any machine, material, or process. Our data-driven approach can be used today, whereas physics-based models can sometimes take years to develop and validate. Our machine learning software can be applied at any scale. It can easily handle these inversions. So physics-based approaches tend to do a really good job going downwards, predicting from modules 1 through 4. They tend to have a more difficult time going up in the inverse, so going from module 4 and predicting to module 3. Because we've taken a data-driven approach, we can easily handle these inversions. Our software can run very quickly on a standard computer, a standard laptop, whereas for some physics-based models, it depends on the complexity of the model, but some of them can take supercomputers, and some of them, we're talking calculations in hours or days, whereas in a data-driven, our machine learning software, we're talking minutes or at most hours. So now I'll walk you through these 4 use cases. And the first use case is determining what process parameters to use in order to achieve a target mechanical performance. So the example I'm going to show you for this use case is F31. This is a use case where the Navy had a target density, and based on that target density, they wanted to predict what process parameters to use in order to achieve that density. The training data set we used in this case were stainless steel 316L cubes that were manufactured on a laser powder bed fusion machine. It was on a Renishaw AM250 machine. We used different parameter sets for each cube. There were 75 specimens total. The parameters we varied included laser power, laser dwell time, and point distance. And again, our material property target was part density. So what our software shows as an output are these quality envelopes. And the 3 black boxes are density values. We've had to redact the density value itself, but they are just imagined density values. And what the software is saying is, if you want to achieve this first top density value, your combination of dwell, distance, and power needs to fall somewhere on this red envelope. As long as your combination of those 3 variables falls somewhere on this red envelope, you will get this target density. If you want the second target density, the combination of those variables needs to be on this yellow envelope. And if you want the third target density, your combination of those variables needs to be on this blue or purple envelope. In this case, we only analyze 3 variables, so that lends itself very nicely to showing graphically, but our software can analyze any number of input variables. So if you want to analyze 10 process parameters, we certainly can do that with our software. The output would not be displayed in graphical form, but you still would get the output telling you what the quality envelopes are for any number of variables that you target and analyze. So that was the first use case. The second use case I'm now going to talk about is the use of in-situ monitoring data to simulate non-destructive tests. So the example I'll show you is in F23, which is where we're looking at visual or thermal irregularities, and we're looking at that to correlate to non-destructive test results. The ultimate goal of this work is to reduce the amount of non-destructive testing that you need to do by training the machine learning software to predict what these results will be. So the types of data we looked at in the examples I'll show you here, for Module 1 data, we looked at the build layout and the planned laser path. For Module 2 data, we looked at high-resolution photos of the build surface and also photodiode data. And what we're doing is predicting Module 3 data, predicting irregularities. So we've developed algorithms that we use, for example, computer vision algorithms, to analyze this in-situ monitoring data in real time. We have parameterized and worked with 2 types of in-situ monitoring data so far, and we will be continuing to expand that portfolio as we go forward. But a look at the 2 types of in-situ monitoring systems we've worked with so far. The first is looking at high-resolution photos of the build surface. So what you're looking at here is a subset of one of these images. The thick red lines on the exterior is the planned laser path. And then if you look very closely, you can see thin red lines in between. That's the hack strategy. And what our computer vision algorithm is doing is picking up on what we call irregularities. So you'll see there are certain hills or streaks or valleys in these images. We're picking up, our computer vision algorithm is picking up on these irregularities. We're then correlating what we see in the high-resolution images to what we see in X-ray CT data, for example. So we're going to be looking at where do we see defects, where do we see pores, and training our machine learning software so that over time it learns when I see irregularities such as this in my high-res images, it tends to lead to a pore, for example. And so what this does when we train the machine learning software, it enables the end user to have this information in real time. So for instance, they could stop the build if they know they're going to get a really big pore that is going to cause the whole build to be not useful, or kind of part of our vision. This is a longer term vision, but it's to make feedback feed forward, where you actually can potentially make corrective actions on the machine as you go. So that's the first type of in-situ monitoring system we've worked with. That actually is on a Pro X320 machine from 3D Systems. The next in-situ monitoring system we've worked with is photodiode data. So here you're looking at a bird's eye view of a build. These are different test coupons, and we're looking at thermal data. So this is temperature. Yellow would be warmer, and blue would be cooler. And again, we're correlating this photodiode data to X-ray CT data and training our machine learning software based upon these correlations. So that was use case number 2. I'm now going to move on to use case number 3, which is all about predicting material properties and mechanical performance. And I'm actually going to show you 2 examples here. The first is F13. So this is an example where our process parameters are set and we're predicting what the density should be. The training data set here was the same that I showed you before. It was the stainless steel 316L cubes on the Renishaw AM250 machine. Again, the process parameters were laser power, laser dwell time, and point distance. And what we're predicting is part density. And what we do, making up the numbers here, but what the software does is, let's say there are 100 data points. What we'll do is we'll train the machine learning software using 70 of those data points, and we will withhold 30 of those data points that the software never sees. So we train the software on these 70 data points, and we then predict what the other 30 data points should be. And after that, we then compare what the predictions were to what the 30 actual withheld values were and see how well the software predicted the results. In this case, we had an R-squared of 0.94, which is very good. This, in this case, means our machine learning software predicted quite well. There are plenty of examples where the machine learning software does not predict well. It really depends on the particular data set, and it depends on how much noise there is in the data. In this particular example, it did predict quite well with an R-squared of 0.94. The next example I'll show you is F14. So this is a case where part orientation is what we were varying, and we were doing that to predict what fatigue life would be. The training data set here was different. We used Ti-6 forest specimens from an electron beam powder bed fusion machine. In this case, I think it was an RCAM A2X machine. We had 4 different orientations that we varied. There was X, Y, XY 45 degrees, and Z. We had 4 builds, and that yielded us 64 total specimens. Again, the process parameter we varied was orientation. And the mechanical performance target that we are predicting is fatigue life. And what our software shows is this predictive model reliability. So in this case, our R-squared was 0.86, which is pretty good. It's not fantastic, but it's pretty good. Now, the software could leave you at that, but it actually goes many steps beyond that. So the R-squared of 0.86 is actually a general predictive number, but the software goes beyond that and actually shows you specific areas where the model is more or less reliable. So the areas that are circled in orange on the screen now are areas where the predictive capabilities of the model are not as good as other areas. On the left circle, this is an area where there's a lot of noise in the data and the data points don't fit to the curve very well. So this is an area where the predictive capabilities potentially could be improved and are not as reliable. On the bottom right is an area where there's actually no training data at all. So the predictive reliability is very low. Another way of looking at this is through a heat map, and what we're looking at here is dark blue are areas of the model that are very reliable, and areas that are red or yellow are areas that are less reliable. And the reason the software shows any of this output is it's all about targeted data collection efforts. So what companies typically do today is they set up a design of experiments and they just follow that design of experiments blindly, doing one build after the next. What our software will do is it actually will show you, based on this information on the screen, it then shows you what your next build should be if you want to improve the predictive model reliability. So what it will say is, hey, you already have great data and great predictive model reliability in this area. Don't bother generating more data in this area. Don't waste your time and don't waste your resources generating that data. What you want to do is generate data in the regions that have less reliable areas. And so the software will be very specific and tell you what to do on your next build in order to be as efficient as possible with your data collection efforts so that you're not wasting time or resources. The fourth and final use case of our machine learning software is all about transfer learning. So this is a concept where, let's say the Navy has a particular machine that they've qualified, and that machine has a specific software version. We will call it software version X. And let's say they've generated 1,000 data points to qualify this machine. What happens when the machine gets a software update, and we're now on software version Y? Do they need to re-qualify the machine from scratch? Do they need to generate 1,000 data points again? The concept of transfer learning and what we're getting at for them is to be able to apply some of the learnings and some of the data from the software version X machine to software version Y. So when the machine gets this update, again, I'm making up the numbers, but maybe they only need to generate 700 data points instead of 1,000 data points. The natural extension thereafter is, what do you do about an entirely different machine? So let's say you generate a lot of data on a 3D systems machine using a particular material. What if you then process that material on an EOS machine? Can you apply some of that data and some of those learnings to the EOS machine? So this is the concept of transfer learning that we're developing for the Navy. Again, this will all be made commercially available. The other concept of transfer learning that is really important is, imagine you have 2 different machines, machine X and machine Y. If you are getting equivalent process signatures, if you're getting equivalent module 2 data from these 2 different machines, that should mean you're getting equivalent material properties, which should mean you're getting equivalent mechanical performance. So the way we think of it is we actually view module 2 data, we call it the universal translator. And this is really important because for the Navy, they want to be able to produce the same part on 2 different machines and know they're going to get equivalent results. So what the schematic on this slide is showing is, on machine X and machine Y, you almost certainly will use different process parameters on those machines. But as long as the process parameters you use in each machine is yielding you equivalent process signatures, that in turn should get you equivalent mechanical performance for whatever part it is that you are designing for. So those are the 4 use cases for our Senvol ML machine learning software. We are going to be running a beta program very soon. It is limited in terms of the number of companies we're allowing in. If that is something that's of interest to you, though, I suggest that you contact us as soon as possible so that we can consider you for potential inclusion in the beta program. Our vision for this software, really quick, is imagine you're a company or an organization, whether you're the Navy or you're Boeing or Northrop, whomever, you're going to have your own instance of this Senvol ML machine learning software, and you have multiple sites, let's say, with different machines. All the sites in your company or organization and all the machines can contribute data into the machine learning software, which means the software will get better and better, and the predictive reliability will get more and more accurate as you continue to generate more and more data across your company. The other benefit of this is that everyone across your organization or company benefits and learns from the data from everyone else within that company, regardless of whether or not they are at the same site or a different site. So that was our Senvol ML software. That's to analyze additive manufacturing data. So today I've gone over how to access additive data, solutions for generating pedigree data for additive, and also our software for analyzing additive manufacturing data. Really quickly, I'm just going to go over our services, and then I will open it up to Q&A. Senvol Services is the consulting division of Senvol. The problem statement here is that there's a shortage of additive expertise in the industry, and additive data expertise in particular is pretty rare. So Senvol Services is the consulting division of Senvol. We have a proven track record of working with top industry organizations, tends to be on data-related projects, though not exclusively. Some of our clients you can look at here, they range and come from companies that are end users, machine and material manufacturers, defense, national labs, government, so on and so forth. So with that said, I know that was a lot of information to digest. I appreciate you all listening in, and thank you for your time. And I'm happy to now open it up to any questions that you have.
All right. Thank you so much, Zach. And that was tremendous information, and there's a lot of it for sure. And we do have a number of questions that came through in the Q&A, the on-screen Q&A. If you don't mind, I'd just like to go through a couple of these.
Yeah, for sure, please.
I'm going to start with some of these more recent questions because I think they're very topical to where you were just now in the presentation on your machine learning. We'll start with this last question here. All the examples you were showing were metals. What about polymers or composites?
The machine learning software is agnostic and can ingest and analyze data from any machine, material, or process. So you're right that the examples were all metals. That's because that's what the Navy is most interested in right now. But our software can analyze data from polymer systems as well.
Okay, excellent. These next two are specific to your machine learning. Do you account for variations in the beam shape, thermal shift, and quality in Module 1? And I'm assuming this is a very specific question, so I'm assuming that the questioner got something.
Yeah. So I think I have a bonus slide that I'll actually show right now. That was good timing. Everything, it doesn't matter what variable you're analyzing, all has uncertainty tied to it. And so we have uncertainty quantification that propagates through the entire model. So for example, you might have a laser power, but your laser power is actually not one specific number. Your laser power is a distribution. And that's going to lead to, for example, a melt pool depth that has a distribution, which will lead to a density that has a distribution, which will lead to a fatigue life that has distribution. So there's uncertainty at every step in the model, in the software, and that it does get propagated throughout.
Okay, excellent. So in relation maybe to this is how do you account for process sensitivity to the build, I'm assuming this is build layout, machine condition, and setting in Module 1?
Scott, I'm not sure I understand that question, so if you could maybe just send me that question along with who asked it, I can follow up directly with that person to make sure I get their question answered.
Yeah, okay, we can do that for sure. So let's jump back into another couple questions here that go earlier in your presentation. How do you decide what input parameters to use for the builds for the Senvol index? For example, machine parameters, scan speed, build position, support structure, et cetera.
Our philosophy is to what I'll call over-track So we track for Senvol index data, and I would recommend anyone generating pedigree data adopt the same mentality, which is that we track any parameter that might theoretically impact results. So there's certain parameters we know will impact results for sure, we track those, but there are also a whole host of parameters that may or may not impact results. And we track anything and everything we can think of. We've seen lots of examples where an organization generates pedigree data and then after the fact realize that the training level of the operator actually made a big difference, but it wasn't something that they tracked, and that ended up being a problem after the fact because it's sometimes data that you can't go back and figure out. In the training case, you could figure it out because you know who the people were, but there are examples where kind of the door shuts and you can't figure it out after the fact. So again, our philosophy is to overtrack and to track as many parameters as we can.
Gotcha. So another question is specific to output. Is Excel the only output format that you offer to customers? I'm assuming this goes way back to some of the earlier.
Yeah, I think that's referring to Senvol indexes. It tends to be an Excel output, but we can customize based on the needs of the customer.
Okay. How large is the Senvol indexes data set? Like how many data points?
So every Senvol index data set is specific to a machine and material combination. The amount of data within a Senvol index data set varies because the test matrix that we do for a particular Senvol index varies from one data set to the next based upon the needs of our customers and industry. So we have some Senvol index data sets where we do many builds and there's lots of data. We have some Senvol indexes where we only did one build and there was only a small amount of data. So it really depends on the specific Senvol index.
Okay. This next one is talking about cost. What is the ROM fraction of a penny in quotes that the TI-64Q20 data would cost?
I cannot answer that on the call, but whoever asked that, please follow up with me directly, or I can follow up with you, and we can discuss more specifically if you're interested in potentially purchasing that data set.
Okay, and we're getting a lot of questions here, so we'll do our best to get answers to all of them, just so people know. But Zach, I know you're very open to questions, so.
Yeah, I want to respect everyone's time, so I know we only have a couple minutes, but if you have a list of the questions, any questions we don't get to on this webinar, I will follow up directly with each and every person who asked a question and make sure all the questions get answered.
Excellent. Zach, you talked a little bit about the mechanical properties of AM parts that are highly dependent on process parameters and conditions. What conditions are used to establish material properties in the Senvol data sets?
I'm not sure if that question is referring to our Senvol index data sets or the Senvol ML machine learning software. For the Senvol indexes, again, we track. In terms of the Senvol ML machine learning software, we can analyze any number of parameters. So if you've captured 40 parameters, we can analyze all of that, and the software will actually output in rank order which parameters impacted the material properties most. So it'll tell you, I'm making this up, but laser power was the most impactful for tensile strength, and so on and so forth. Then we'll rank order them and show the marginal contribution of each parameter. Some parameters may not impact the result at all, and our machine learning software will show that.
Okay, we're going to have to wind this up. Zach, if you wouldn't mind, we would love to provide you the information, provide you these questions, and possibly even in some method we could feed back to everybody that's been on the call with some of the answers. I realize that in some cases, such as the rough order of magnitude question around cost, that those could be sensitive and can be private conversations that you would have with anyone that's asking. We'll do our best to make sure we get these questions answered. This is important stuff. This is great material that you've gone over. We thank you so much for taking the time as a good friend of America Makes and as a longtime member and partner with us. One of the things, though, I do want to mention, I'd be remiss if I didn't at least mention our TRX event next week in Austin, Texas. Zach, you're going to be at this, aren't you?
Yes, I will be there.
Yeah, so I mean, anybody that's on the call that is going to be there could even follow up with you at this event. The TRX events are live, or for anybody on the call that's not aware, TRX events are the live iteration of the TRX webinars. We actually started with events and we've moved into these webinars. But it's a way that we can have constructive exchange of technical information from leading experts on various topics. This particular TRX in Austin will be held at the EOS facility in Pflugerville, and will focus specifically on supply chain and the needs of the supply chain. If you're interested, check it out on the website. There are very limited numbers of seats left. I think registration deadline is tomorrow, if I'm not mistaken. There are a few seats left. If you're interested, I would recommend you hurry up and get yourself signed up. It's a terrific event. Look at the agenda. There's some terrific speakers, and it's a great way to interact with America Makes and our memberships. So thank you again, Zach. I think we're going to wrap it up here. For those of you that are on the call that had questions unanswered, we're going to do our best to filter these questions back to everyone with Zach's help and support. We look forward to that. Zach, do you have anything else?
Yeah, I'd just like to thank America Makes again for hosting the webinar, and I'd like to thank all of you for spending your time engaging on the topic. If you do have any further questions at all, please don't hesitate to contact us at info@senvol.com. Thank you very much, Scott.
All right, thank you, Zach, and have a terrific day. And everyone that's on the call, like I said, if you're interested in the TRX event, please check it out on the website. Go to americamakes.us. And we thank everybody for their time. This has been a terrific presentation. Thank you, Zach, and we'll close it with that.